So hello everyone, this is our third session. Today we will do P and PI controllers at the first exercise. In the second exercise we will consider also PID controllers. So let's start. Consider the following control setup using control system toolbox. We have three systems here. So the controller, the system itself, it's also called plant model, sensor. We have to apply 20 degrees Celsius as a reference signal here. We have to simulate the responses at the system output here, at the measured output here, and also here at the error level. The reference signal is also called set point signal. Process value, the system output, and the measured output is also called measured process value. Okay. Let's start. I strongly recommend that you start all your MATLAB codes with clear or close or, just to avoid any mistakes. Then we have to define the simulation parameters such as the sampling frequency, maximum time. We have to generate a time scale between 0 and Tmax. And we have to generate the set point reference signal. So if you just look at it, it's nothing else, just a step signal multiplied with 20. Then we go for the transfer functions. So I'm going to use symbolic notation. So S equals to TF of S. Then we have the controller. At the moment it's just a constant. Then we have the system. And you notice that we have this exponential part. This is the dead time, the delay. If you want to use the classical notation to generate a transfer function, you can use the TF command, and the delay you should set as input delay, as you can see here in the code. Then we have the sensor. Two important functions. We have the closed loop system here. You can use the feedback command or manual notation. If we go back, so what we have basically is these terms, the controller system, divided with the open loop gain function. The open loop gain function is defined here. What is important to notice that we set the controller to 1. So actually it doesn't do anything at the moment, but later on we will override this value to something else. Then the next that we have to calculate the responses. So we have the response here, system output is nothing else as just a step response of the closed loop system. We use here lsim. If you wish, you can use still the step command, but you have to multiply them with 20. Then we have the measured output. This is what is picked up by our sensor. Then what we have to do here, that we take the closed loop transfer function. So this is the transfer function between the reference and the system output. So we are here, and we multiply with the sensor transfer function. This you can see here. Then the error signal is the reference signal, so this 20 minus the measured output. The next steps are very simple, so I make a new figure, I plot these quantities, and this you can see in the first figure. So here we have the reference output, measured output, and the error signal. The analysis now is not important. As you can see, the system is clearly unstable. Then we go for the second point. Display the body plot of the underlying system and compare the results with margin command. So this is my body plot, and first we have to look for the crossover frequency. So it's at the 0 decibel magnitude. It's more or less here at 0.76 rad per sec. And when I go here, I see that the phase there is minus 465 degrees. So the system is stable if you have positive phase margin. So we compare the phase to minus 180. If the phase margin is positive, let's say at least 45 degrees, then we have a stable system, otherwise it's unstable. And now the surprising thing, when we compare the margin results of the margin comment, you can see that it thinks that our system is stable because it has a positive phase margin. But clearly we can see that it's a bad reading. So pay attention, automated tools sometimes give you wrong result. The stability issues you can also see in the step responses. So that was in short the first part.